Okay, so today we're going to talk about one last method to solve for partition functions, which is actually the simplest and the most famous, and actually also the first one you always try when you don't know what to do. And it's called mean field theory. Now, mean field theory is based on the following idea. I will explain mean field theory using the easy model as an example, but it can be applied to the Potts model, to anything you want, right? Even to models with continuous statistical variables. So let us consider, for example, the following model. Which is an easy model in a magnetic field, where here I have interaction between nearest neighbors in some lattice. For example, my lattice could be, I don't know, a triangular lattice, in which case I would have, let's see if I'm able to draw a triangular lattice. So it should be like this. So in this case, you would have that if this is your spin, the nearest neighbors are all the guys that stay around it. So this one, this one, this one, this one, this one. You have 6 nearest neighbors, okay? All the guys sitting around an hexagon around your spin. Now, the main idea of mean field theory is the following. If you look at this interaction term, this one, then you see that the typical term is going to look like this. It's going to be some spin, let's write it in red, sigma, no, not red, not in blue, sigma, interacting with the sum of all the nearest neighbors of sigma of the sigma i's. You see? Times j over 2, of course. Minus j over 2. So every time I have a sigma appearing, all the nearest neighbors will appear interacting with it. Right? Now, what happens is that these nearest neighbors will have different statistical configurations and will fluctuate, right? Among different statistical configurations you are summing upon. But the point is the following. If you're essentially summing over, not independent, but over many variables, right? Many statistical variables. Now, you can think that in a situation in which the number of these variables is very, very large, right? The probability distribution of this function here, let's call it sigma, so the probability of this sigma is going to be a function that is going to be peaked around some average value, sigma average, with fluctuations, these fluctuations, sigma, that scale like what?
1 over square root of n or something like that.
Well, that is the relative fluctuations. So the fluctuations will scale, sorry, the variance, the width, sorry, What is it? The square root is the standard deviation.
Yeah.
So the standard deviation will scale like what? The number of what? We will scale like the number of nearest neighbors. That's correct. But like, so the sigma squared, which is the variance, will scale like the number of nearest neighbors. The standard deviation, which is the width, will scale like the square root of the number of nearest neighbors. Square root of number of nearest neighbors, which is known as the coordination number, and typically for the coordination number of a lattice, you use the letter z, little z. Okay? Is it clear to everybody, this story? Kind of? Well, we have seen that because of central limit theorem, when you have central limit theorem, what do you expect? You expect that if you have x, which is the sum over independent variables, then the average of x is going to go like n average of little x, and the standard deviation, the fluctuations, the variance, is going to go like n times something, right? Also scales with n. And therefore, if you take now the square root, which is the standard deviation, this will scale like square root of n. Now, what is n in our case? N is the number of terms that appear in this sum, which is the number of nearest neighbors of sigma, which is the coordination number z, right? So that's why we do expect this to scale like this. But then we have a situation in which the average will scale like z, the variance will scale like, standard deviation will scale like square root of z, and therefore the relative fluctuations will scale like 1 over square root of z, and in the limit of z going to infinity, z being very, very large, will go to 0. So this function, p of sigma, is going to be strongly peaked around the average value. You see? That's the logic. Now, therefore, you see what I mean?
Yeah.
So therefore, is it clear to everybody, this story? Perhaps sometimes only on even days, or it's clear. I can repeat it. If it's not clear, I can repeat it. Clear. Okay. So now that this is clear, then it's also clear if I now replace in this thing here, I would take this and replace it with this sigma with average sigma, right? Which is essentially the average magnetic field that is generated by the surrounding spins on the spin I'm looking at. This approximation would be exact in the limit in which the number of spins I'm summing upon is very, very large, right? Now, there are two limits in which this is true. One limit is when the coordination number z, so limits in which mean field theory is going to be exact. So one limit is when the coordination number is very, very large, goes to infinity. So what is the coordination number very, very large?
For big dimensions.
In big dimensions, exactly. Think about a square lattice. In 2 dimensions, the coordination, in 1 dimension, the coordination number is 2. In 2 dimensions is 4. In 3 dimensions is 6. and so on and so far. It's going to grow in 4 dimensions, it's going to be 8, I suspect, and so on and so forth. And therefore, in the limit of very, very large dimensionality, which might be something not really physical, but we will understand in a second why this is important. In the limit of very large dimensionality, I don't know, 10 dimensions, right? Then we can suspect that mean field theory for the easy model is going to be very, very good, okay? There is another limit which is a bit more physical than large dimensions. So this is large T. So you want your spin to be coupled to a big number of other spins. Now this happens when your interactions are not nearest neighbors, but are, for example, long-range interactions. When you have long-range interactions, then this guy doesn't see only the guys who are surrounding it, but sees all the guys in the lattice. And therefore, with long-range interactions, you can suspect that mean field theory is going to be exact, right? So long-range interactions. This is 1, 2 is long-range interactions. So these are the 2 limits in which we do expect mean field theory to be correct. Now, in practice now, how do we do mean field theory? Well, let us mean field theory in practice. So up to now we've been doing what I call blah blah blah. A lot of words and no calculations. So now we will do the calculations. So let us introduce the following thing: the magnetization, the average magnetization per site, defined as follows. And now let me change variables and call sigma I equal to m plus sigma I minus n. So this is the average magnetization plus the fluctuations, the small fluctuations on top of the average magnetization. You see? This, let's call it delta mi. And now let us take our easy model and let us substitute the expression we just found for sigma I, right? So if we do this, we get that this is equal to what? Well, we have to be careful. So if I do it, for example, on this term, sigma I times sigma j, I will get that sigma I times sigma j is equal to m squared plus delta mi sigma j plus delta mj sigma I plus delta mi delta mj. Right? But now I assume that my delta m is small. The fluctuations on top of the mean field are very, very small, which is exactly the same logic as what I told you before, assuming that fluctuations are tiny, tiny. And therefore, if they are small, I can take this quadratic term, think of this as an expansion, take this quadratic term and neglect it. Now, if I neglect the quadratic term, I go back to what is written here, and what I get, go to the next page, is that this is equal to minus j over 2, sum over I and j, m squared plus m delta mi plus m delta nj minus b sum over I sigma I. Okay? So now, remember that now, what is delta mi? This was m minus, sorry, the other way around. Delta mi was sigma I minus m. This was equal to sigma j minus m. If you substitute these two expressions and do some quick algebra, you will easily get that this is equal to j over 2 sum over I and j m squared minus j over 2 sum over I and j and sigma I plus sigma j minus b sum over I sigma I, which you can rewrite as, okay, so this sum here is going to be equal to n times n squared?
n minus 1.
No, because this sum is over the nearest neighbors. So what is going to be the result of this sum? M is always the same, so it's going to be j.
Are we on the cube? On triangular lattices.
Not triangular, on any lattice, I don't care.
Coordination number times the number of sides.
Exactly, it's going to be equal to the coordination number times the number of sides. It's going to be equal to n, and then for each n, for each side, you have z nearest neighbors. So therefore, it's going to be equal to n times z, right? While the other term is going to be minus. So here I have two terms. These are dummy indices, so I can exchange here j with I. I get a factor of 2 that cancels this one, and therefore I get minus j sum over I and j m sigma I minus b sum over I sigma I. And now, well, life is simple because you see here I have a sum over I and j. Well, I is fixed, I give it here. When it's sum over j, I have only the nearest neighbors, so I get a factor of z in front. I will have j over 2 m squared n times z minus j times m times z plus b sum over I sigma I here, right? So it looks like as if I essentially took a theory in which, a model in which I had interacting spins, and now I have non-interacting spins, right? But the trick is now that these non-interacting spins are actually not non-interacting. They're interacting through the mean field M that should be determined self-consistently. Okay? So how do you determine? Well, you remember that so M should be determined self-consistently. So what you do is you say, well, look, M is equal to what? Is equal to 1 over n sum over I sigma I. Well, I know how to compute sigma, this average, in the statistical ensemble that is given by this Hamiltonian, right? You see, let's call this Hamiltonian here H mean field. This is not an H, this is an M, so let me rewrite. Let's be fancy. H mean field. Okay? So this would be equal to sum over I sigma I e to the minus beta H mean field divided by, well, our usual sum over I e to the minus beta h. Okay? So now you see that if I use this h mean field to calculate this average, is straightforward. What you will get is a tangent hyperbolic, right? And nothing else. Because on top you will get e to the beta, well, e to the beta effective magnetic field times sigma, effective magnetic field, minus e to the beta, minus beta effective magnetic field, and the minus comes from this guy here, and on top you will get a plus. So it's a sine hyperbolic divided by a cosine hyperbolic. If you're not convinced, you are more than welcome to just do it. And you will get the result tangent hyperbolic of beta times j n z plus b. Okay? So in other words, the self-consistency condition gives you an equation, a nonlinear equation for m. M is the unknown. Let's put it here in red. So M is our unknown that we have to solve, and once we solve it, we have solved essentially the Limfield theorem. We know everything about our system. Clear? It's very, very simple. All right, so the first thing I would like you to notice, there are two things I would like you to notice. First of all, thing number one. No, actually, this is the most important thing. The self-consistently conditions, I didn't write it and spell it in letters because it's important. What? Everything is buzzing. My phone, my watch. Self-consistency condition determines the minimum of the free energy. Okay? This is crucially important. It's the first time that you see actually in practice working the principle we've been discussing so many times, that physical states, physical equilibrium states are actually the minima of the free energy given the parameters that you're putting in your system. Now, how do you check this? Well, you know how to check it. You know that this is H mean field. Given H mean field, I can compute the partition function Z mean field, which is given by sum over sigma I e to the minus beta H mean field. And computing this partition function, I can compute what is the free energy. So I can set it equal to e to the minus beta F, right? So what will I get? Well, for the partition function itself, it's straightforward. It's a partition function of independent spins. So you will get e to the minus beta j n z over 2 times m squared. This is just a constant term that was in front of my Hamiltonian times the term of all the spins, independent spins in a magnetic field. It's a calculation that we have already done some time ago. And you will get twice the cosine hyperbolic of beta j n z plus b to the power n. Right? Clear? Great. Now, this said, well, we can easily compute what is the free energy. I'll let you do it. It's straightforward. It's not something I think we should. It's a log. This free energy is minus 1 on the beta log. And now let us take derivatives. df, dn. We want to. So the statement is the minima of f with respect to m, with respect to the variable m, are the physical states. So are essentially the solution of the mean field theory. dm df, you take this derivative, what do you get? Well, you get j n z times n. So this is the term that comes from this quadratic term here. Times m minus the tangent hyperbolic of beta times j n z plus b. Okay? So you see that if I set this equal to 0, this stuff here equal to 0, I obtain exactly the equation that I wrote down as the self-consistency condition for the mean field theory. So, therefore, the extrema of the free energy are the states I was interested in. However, we have to be careful, because when I talk about free energy, I'm always talking about minima of the free energy, not maxima, right? When you solve this equation, you will catch both minima and maxima of the free energy without distinction, because you're setting the derivative equal to 0. Therefore, if I want to determine which one of the solutions of this equation represent the physical states of my system, I have to study also the second derivative, right? And determine whether it's positive or negative, right? If I take the second derivative, so here I have my d j di, and the second derivative is going to have the same letters. So I get j n z times 1 minus beta jz plus beta jz tangent hyperbolic of beta j and z plus b squared. Okay? Great. So now we know, therefore, that we have to solve so more precisely, because before we just wrote a self-consistency condition, but from this analysis, we know that we have to solve this equation, solve it, and then we have to get the solutions of this equation that represent minima, and therefore such that the second derivative is positive. Okay? That's it. All right. Now, let us try to solve this equation, to solve the self-consistency condition in the case where b is equal to 0. You're more than welcome to solving it in all possible cases. You will see that you will get some interesting stuff. I'll tell you later what you will get, but this is actually the simplest possible situation. So in this case, I have a self-consistency condition, which is this one. Beta j z. Okay? Now, you see that since the tangent hyperbolic at 0 is equal to 0, m equals 0 is always a solution. Right? However, if I take this equation here, you see, and I set m, b is equal to 0, m is equal to 0, this comes out to be 0, this stuff. And here I get 1 minus beta jz, right? So, therefore, the second derivative at b equals 0 is equal to j times n times z times 1 minus beta jz. Okay, so now, you see that if beta Jz is smaller than 1, which means that T is greater than a critical temperature Tc, which is equal to J times Z. Okay? Because beta is 1 over T up to a K Boltzmann, which is equal to 1 for us. Then m equals 0 is a minimum. If instead beta Jz is greater than 1, which means that T is smaller than Tc, then m equals 0 is a maximum. So in other words, if I would plot the free energy, no, it's great. So if I plot the free energy is always infinite. So this is F, this is M. The free energy always goes to infinity. At m going to plus infinity or m going to minus infinity, right? So it's going to go like this, like that. Now, for t greater than Tc, Z is going to be positive, the second derivative, and therefore the free energy is just going to be a nice, positive curvature figure like this one. For J negative, what is going to happen is that your free energy is going to have a negative curvature at this point, which most probably will make it have, we will see it later on, a behavior like this. Okay? So we should have two solutions. And this is indeed the case, as you can see by looking at our original equation, this one. Why? I took the other one. No. Just a second, guys. Okay. So if we look at this, then you see that if you try graphically to solve this equation, so it's a tangent hyperbolic, so it should look like this, it should go to -1, no, -1, then go like that, then go to +1. But the slope at close to m equals 0 is determined by this coefficient, this one. While here you have just a straight line, okay? So this straight line, let's draw it here, like this. You see that if t is smaller than Tc, if t is greater than Tc, then this coefficient is smaller than 1, and therefore you have a tangent hyperbolic that will look like this one. Sorry. If this happens, therefore, t is greater than Tc, you have only one solution at m equals 0. If instead t is greater than Tc, you will have a tangent hyperbolic that looks like this one. And you have three solutions. T is smaller than Tc. One at positive m, one at negative m, so m minus m bar, and one at 0. The one at 0 represents an unstable state, is not the minimum. The two solutions at positive and negative m, which are connected by symmetry, represent two physical states. Okay? Now, in practice, what this is representing is a classical situation in which you do have a phase transition. It's actually a second-order phase transition. Silvia will give you a lecture on the classification of phase transitions in thermodynamics, etc., etc. But this is a second order phase transition with an order parameter m that is continuous at the critical point. And what you see is that as you cross this critical temperature, you have that your system breaks spontaneously a symmetry, which is the symmetry of inversion in your Hamiltonian, right? The symmetry that tells you that if all sigmas go to minus sigma, then the energy is invariant. But these states, which are the physical states, are not invariant under this symmetry. Okay? And that's the main point. That's why it's called a spontaneous symmetry breaking. So when you should be excited, because when you take your wallet and you take out your credit card, then you have a spontaneously symmetry broken state in this stripe here, right? And if you don't have it, then it doesn't work. So it's a useless credit card. And this is actually a ferromagnet with a very high coercive field, which means you need a very high magnetic field to demagnetize it, otherwise it would be useless. And in addition to this, the critical temperature at which you melt ferromagnetic order for these stripes, for all the stripes of credit cards, is, if I'm not mistaken, about 500 degrees Celsius, which means that in practice you would first melt the card and then melt the magnetic order. So it's pretty useless to do the experiment. But you see that in practice it's actually something useful. It's something we use all the time. But we have to be careful in putting them close to a cell phone, because we can actually demagnetize them with cell phones. All right. So credit cards are actually an example of spontaneously broken symmetry state. All right. So now, what can I do now with this? So now that I understand that there is this phase transition, I have two solutions. They break the symmetry. If I follow one solution and I plot it as a function of, let's say, of temperature, I would get a figure that looks like this. So this is temperature, this is Tc, and I would get something that looks like this. You can do it on a computer if you don't believe me, but you will see that it looks like this. Now, what is interesting is to compute the way the magnetization vanishes at the critical point. I will explain you in a second why it is important to do that. So let us compute how the magnetization vanishes at the critical point. Well, let's go back to the equation. The equation was, is written up here. So let's write it as m equal to tangent hyperbolic of...
Sorry, is that like absolute m?
Which one?
In the second plot.
Oh, I'm just following one of these solutions. So let's pick up the positive one and you follow it. Of course, there is also a one in which you're negative and you go to 0. But, the point is that since this is a symmetry broken state, your physical system, like the credit card, is going to sit in one of these two minima. It cannot sit in both, right? It's going to sit in one of them, and it's going to stay there. And then if you change the parameters of your system, for example, the temperature, the solution is going to be distorted the following, if you start positive, you're always going to be positive. That's what I mean. Okay? So the physical system is not in a superposition of the two minima, it's in one of them. It's decided by the dynamics, how it got there, etc., by a history that you don't want to know, but is certainly in one of those two guys, in the thermodynamic liquid. All right, so this I can write it as Tc over T times m. Or in other words, I can rewrite this as m equal to T over Tc times the arctangent hyperbolic of m. I just inverted it, right? And now t over tc, I can write it as 1 plus t minus tc divided by tc. I just rewrote it. You see, it's just some. Now, this quantity here is what people call, in the theory of phase transitions, with the letter T, reduced temperature. Right? Why reduced temperature? Because it's essentially the deviation from the critical temperature on a scale set by the critical temperature itself. So it's how far away you are from the critical point. So now you see that if I now rewrite expand, so close to the critical point, close to Tc, m is small, goes to 0. Therefore I can expand this arctangent hyperbolic in power series, and I will get m equal to 1 plus t times, so the expansion of the which is m plus m cubed divided by 3, and this I can just solve it. I will find m, an equation m cubed equal to minus 3t times m, and therefore m equals 0 is always a solution, and then you have two solutions, m equal to plus and minus 3t to the power 1/2, right? So the minus t is because the temperature has to be smaller than the critical temperature in order to get these solutions, so the reduced temperature has to be negative, and you see that m goes like minus t to the 1/2 up to some constants, okay? Now this is the first time you see, probably, I don't know if you have already seen it in your previous studies, something that is known as a critical exponent. Okay? Beta, this beta here, is a critical exponent. What does it mean? It's essentially telling you, so second order phase transitions are characterized by the fact that you can define an order parameter, such as the magnetization here, and this order parameter at the critical point vanishes, okay? As in this case, this is a ferromagnet to paramagnet phase transition. So the ferromagnetic order is our order parameter, so magnetization. And now we are trying to find how the magnetic field, the magnetization vanishes at the critical point, and it vanishes as a power law with this characteristic exponent beta. Now, if you would compute, for example, the susceptibility, which is how much the magnetization varies with a magnetic field, this is something that you can do by putting back the magnetic field and solving self-consistency equations. But if you compute this susceptibility at b equals 0, you will find that this goes like t, absolute value, t to the minus 1. Okay? So the susceptibility diverges close to the critical point. This is another example of what people call a critical exponent. It's called in general gamma. Another critical exponent. Now, the fact that the susceptibility diverges, what is a susceptibility? I always explain the susceptibility with a very simple example. Suppose that you're in a car, right? And you want to decide by how much the car will accelerate by stepping a bit on the pedal. You know what is the pedal of the car, right? So if you put some pressure on the pedal and you're sitting on a Fiat Panda, the car will reach probably 50 kilometers per hour, right? If you put a tiny bit of pressure on the pedal and you're sitting on a Ferrari, on a Formula One Ferrari, well, the Formula One Ferrari doesn't have the pedal, but on a, some other Ferrari, then the car will easily reach 150 kilometers per hour, which means that the car, the Ferrari, is much more susceptible to your pressure than the Panda, right? Clear? Okay, so this equation here means that a magnet close to a phase transition is like a super Ferrari. You put a tiny bit of magnetic field and poof, you get a huge magnetization as a result. If you're away, because the susceptibility diverges, right? If you're away from the critical point, very far away, then you put a magnetic field and the guy has hard time to order in the direction, okay? So that's the meaning of the divergent susceptibility. Now, there is an important thing about these critical exponents. In mean field theory, we just found that beta is equal to 1/2, and we found that gamma is equal to 1, and that's it, okay? This is the mean field theory of our easy model. Now you can ask me, okay, so what about real physics? I mean, not approximations. Suppose that we take the easy model in various dimensions. Can you compute what is beta and what is gamma? You will have a phase transitions apart from one dimension. We know that in one dimension we don't have phase transitions, right? You remember the Pyers argument. But in 2 dimensions, 3 dimensions, 4 dimensions, 5, 6, 7, 8, 9, 10, you will always have a phase transition. The question is, what are these 2 critical exponents? So let us make a table. So, and let us write up in the various dimensionalities. So this is the dimension, let's say 2, 3, 4, 5. This is beta and this is gamma. Alright, let's start with 2 dimensions. In 2 dimensions, the model is exactly solvable. It was solved exactly by Mr. Onsager, and you know that it can be exactly solved because I told you that the transfer matrix is equivalent to the one-dimensional quantum Ising chain, which is an integrable model, etc., etc. That you know. You can impress your friends by saying this. Now, the beta and the gamma can be calculated exactly, and you get out 1/8 and 7/4. Well, so then you compare this with this, and you see that if I would have done mean field theory, yes, I got a phase transition, but the beta and the gamma that I got are very far off. They're not even close to be correct, right? I mean, 7/4 is a bit more than 1, it's closer to 2 than to 1. 1/8 is closer to 0 than to 1/2, etc., etc., etc. You go to 3 dimensions, and then you get 0.324 and 1.239. Alright? So you see that in 3 dimensions you're getting a bit closer to mean field theory, but you're not yet getting mean field theory. Not at all. Right? That is something. In 3 dimensions, the calculation cannot be done exactly, so there are various techniques to get approximate results, computer simulations, etc., etc. That's, those are some approximations. But in 4 dimensions, lo and behold, you get 1/2 and 1. And in 5 dimensions, you get the same. And in 6 dimensions, the same. You know already this stuff, right? Who told you? Okay, so above, for the easy model, above 4 dimensions, you always get, for the critical exponents, the mean field results. Okay? So that's why for the easy model, 4 dimensions is called the upper critical dimension. What does it mean, upper critical dimension? Is the dimension up to which mean field theory is wrong and above which mean field theory is exact, including that dimensionality. So for the easy model, 2 and 3 dimensions are not mean field, 4, 5, 6, up to whatever you want is always mean field theory is correct. Unfortunately, our credit cards do not have 4-dimensional ferromagnets, right? So 4-dimensional ferromagnets are not that physical, but it's important to know. Now, there is another thing that is called the lower critical dimension. For a phase transition, which is the dimensionality below which there is no phase transition at all. And for the easy model, this lower critical dimension is 1, right? So 2-dimension and 3-dimension, you have a phase transition, but it's not mean field. Above 4 dimensions, you do have a phase transition, but everything is described by mean field theory. Now, you can ask yourself, let me tell you something that is quite advanced. So, it's again like Italian opera. So, you can ask me, why are you wasting your time to compute these critical exponents, right? Why should we waste our time to do all kinds of simulations and make tables of critical exponents for the easy model, which is a model which is oversimplified and is hopeless if you want to describe a real material that is ferromagnetic, like the magnet we use to stick something to your fridge. Okay? Now the reason is something called universality. What is universality? Universality means the following. If you take a system that has a phase transition, and you have that the order parameter has a certain symmetry, for example, in this case the order parameter has inversion symmetry, right? Then all the physical systems that are in that dimensionality and have an order parameter that has that symmetry, no matter what are the microscopic interactions, the lattice structure, the type of atoms, electrons, conductors, this and that, and all the details will have the same critical exponents. Okay? So that's why people wasted their life computing. I mean, not me, but there are some people who actually spent their life computing critical exponents. The reason is that they are universal. So you pick 2 ferromagnets, which are very different, have a different crystal structure, a different materials, different atoms, different chemical bonds, different type of interactions. But they are both 3-dimensional, and they have both uniaxial symmetry, which means that they have this order parameter that has inversion symmetry. Close to the critical point, the order parameter will vanish with this critical exponent in both cases. And the susceptibility will diverge with this critical exponent in both cases. And, most importantly, you can predict this by an oversimplified model such as the Ising model, in which you are not taking into account the crystal structure, you are not taking into account the type of interactions, you don't care about what type of atoms, you don't do ab initio calculations, yet the critical exponents come out correctly. Okay? So this is universality. Something very, very special. It's actually in my view, is actually the most important thing in theoretical physics. Because if you think deeply about it, you realize that if it wouldn't be for this reason, doing statistical mechanics in most cases would be a waste of time, right? Because you would have, in order to describe really a material, you would have to describe all the precise interactions, all the precise bonds, to do all the time an ab initio calculation, which is, it's a lot of work. Instead, we can do statistical mechanics with simple models, like easy model, Potts model, etc., because the only thing that matters is symmetry and dimensionality, and nothing else. So this is really special, something peculiar of modern physics. All right, so now after this poetic part, let us now do some other calculation. So I promised that mean field theory was exact in two limits. One limit is the limit of large dimensions. The second limit is the limit of long-range interactions. Let us now see what happens with, redo the calculation with long-range interactions in a slightly different way to see what comes out. So, long range. So, by the way, all this stuff of universality is explained theoretically by something called renormalization group, which is the subject of a course that I do at CISA. So for the PhD students, maybe those of you will perhaps come to CISA next year. Usually, few people come, so you're more than welcome to come and listen to those lectures if you're interested. All right, so mean field theory for long-range interacting systems. So let us consider now a system in which I don't have, I do have infinite range interrupts. So I have something like this: J, sigma I, sigma J, minus beta, sum over I, sigma I. Now, so here I and J are not restricted anymore to be nearest neighbors, right? They actually can range over the whole lattice, which means that everybody is interacting with everybody else, right? Now, but you see that there is a problem, because if everybody is interacting with everybody else, this term in the interaction will scale like n squared, because it's the number of pairs I can create, right? So this term in the energy will scale like n squared, while this one is extensive, right? Scales like n. Well, this implies that in practice, I will have that if so when I go to the thermodynamic limit, this term here will always dominate over this one, no matter what, because something grows like n squared, that's it. So you're never going to see a magnetic field in the thermodynamic limit. In order to avoid this problem, typically when you consider a model with infinite range interactions, what you do is you use what is known as the Katz normalization. So you just divide your interaction by n. And this n is called Katz normalization. Which is put there in order to guarantee that the energy is extensive, not super extensive. All right. So now, once I put the Katz normalization, you see that this can be written as follows: minus j over 2n, sum over I sigma I, times sum over j sigma j, minus b sum over I sigma I, right? Since everybody is interacting with everybody else. Which means that if I now define this as m, this is equal to minus j over 2n times m squared minus b times n. M is a collective variable, this is the magnetization. Okay? Now, I did not even specify the lattice because everybody is interacting with everybody else, so there is no spatial structure to my interaction. Now, what is M now? M is sum over I, sigma I. Now, if you think for a second, we already did this calculation some time ago as an example. So, if you think for a second, this is going to be equal to the number of spins with plus magnetization minus the number of spins with negative magnetization, right? And nothing else. So, in other words, I can rewrite this as, if I plug in this expression, as minus j over 2n, n plus minus n minus squared, minus b, n plus minus n minus. Okay? Now, this for the energy, right? Let us now calculate the entropy. For each given energy, so for each given n plus and n minus, what is the entropy? The entropy is going to be equal to K Boltzmann, the log of n factorial divided by n plus factorial times n minus factorial. Clear? Which is the number of ways to select n plus spins in a sample of n spins. So this is going to come out to be equal to sorry. Yes. K Boltzmann log of n factorial divided by n plus factorial n minus factorial. And this you do the usual stuff, Stirling approximation, etc., Stirling. And you will get K Boltzmann n log n minus n plus log n plus minus n minus log n minus. Okay? And now, since I have the energy and I have the entropy, I have the free energy.
Sorry, at this point we already assume that we are far away from the critical point because of the Stirling approximation.
Right, far away from the critical point. The problem, the critical point is not a problem. The problem is zero temperature. The problem is zero temperature because at zero temperature all the spins are going to be up and
But
none
we
is
have
going to
magnetic
be
field.
down.
We do have magnetic field.
Yeah, okay,
and if the temperature is significantly low, then n plus might be, of course, it will be larger.
okay, so we are assuming that there are some significant fluctuations in the magnetization. You're absolutely right. Otherwise, Stirling doesn't make any sense, right? So we are assuming that we are significantly far from any stuff like that. All right. So now, let us compute the free energy. And the free energy is going to be a function of two variables. It's going to be a function of n plus and n minus. Or if you want, it's going to be a function of, I can normalize both of them by n and call these two guys x plus and x minus. Okay? Now, if I do this, then I can rewrite my energy H. Well, it's just a matter of doing a quick calculation. Here you put in, here you multiply and divide by n, and you put the n squared inside. And here you multiply and divide by n, and you put the n inside. And you see that you will get at the end minus n times j x plus minus x minus squared minus b plus b x plus minus x minus. And the entropy, you have to work a bit harder, but it's not a big deal. comes out to be k Boltzmann n x plus log x plus x minus log x minus, which is positive because x plus and x minus is both smaller than 1. Okay? Now you combine these two guys and you write the, you combine this and that and you write the free energy, and you get minus n times j over 2. Why j over 2? No, there's no j. Yes, sorry, here there was a j over 2. Minus j over 2 x plus minus x minus squared minus 1 over beta x plus log x plus x minus log x minus, where I set B, the magnetic field, equal to 0. Okay? Clear? And now this comes out to be equal to 2 watts. Well, let's look at this for a second. You see, x plus is n plus divided by n, x minus is n minus divided by n. Of course, they satisfy a constraint which is not taken into account here. And the constraint is that x plus plus x minus is equal to 1, right? Therefore, if I want to characterize what is the magnetization, the spontaneous magnetization that is generated in my system, which is x plus minus x minus, I can rewrite x plus as 1 plus delta x divided by 2, x minus as 1 minus delta x divided by 2, and I will have that my magnetization n is equal to n delta x, right? Here. Now, if I substitute this parameterization in here, I will get that the free energy is a function of delta x, which is essentially the magnetization. And now, in order to find what is the state that blah, 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 I have to minimize this function over delta x, right? And that will be the physical state that is attained by my system. So, now, the free energy as a function of delta x is equal to minus beta times n j over 2 delta x squared plus minus just a second. There's something wrong here. There is a beta missing. No, 1 over beta. No, it's okay. It's okay. Well, let me just write down for you the derivative. So if you take the derivative of f with respect to delta x, I'll let you do the calculation. What you will get is that this is minus beta times n times jb delta x minus 1/2 log of 1 plus delta x divided by 1 minus delta x. Just do the calculation. Okay? And now, what you see is that you have to set this equal to 0. But look at what happens. This function here is essentially the arctangent hyperbolic of delta x. It's another way to write the arctangent hyperbolic. And therefore, what I got when I tried to solve this equation is j times p delta x equal to the arctangent hyperbolic of delta x. Or, in other words, delta x equal to tangent hyperbolic of beta j delta x, which is essentially the same equation as the one I got before. Right? Now you can ask me, what is the meaning in this particular case of looking at the minimum of the free energy? Right? It's saying the minimum of the free energy is the physical state that is realized when I exist. Now the meaning is the following. When I compute the partition function, right? So the partition function is the sum over all configuration of sigmas e to the minus beta h. But h is a function of only n plus and n minus, as we have seen, right? Therefore, I can write this as a sum over all n plus and minus, then as a sum over all configurations that produce a certain pair n plus and minus, okay, of e to the minus beta h n plus and minus. But what is the sum of all configurations that give us a blah blah n plus and minus? This is, n choose n plus, right? So this is going to be equal to sum over n plus n minus, subject to the constraint of summing to n, of n factorial divided by n plus factorial n minus factorial e to the minus beta h, right? But this is equal to what? This is equal to sum over n plus n minus e to the minus beta h minus t times s. You see? Because s is k Boltzmann log of n factorial divided by n plus factorial divided by n minus factorial. And now you see that when I minimize the free energy, I'm essentially doing for this sum the saddle point approximation. Okay? I'm saying this sum is going to be dominated by the term in which this object here is minimum. Why? Because it's extensive, right? There is a net in front of everything, so I have to minimize this term, and this term, minimum, is going to dominate the whole sum. So this is going to be approximately e to the minus beta n times the free energy density at the minimum. So that's the logic. All right? So for a system that has infinite range interactions, mean field theory in the thermodynamic limit is not only a good approximation, is exact. Is an exact approximation, is an exact calculation. Right? If you have a finite size system, then there might be fluctuations. But in the thermodynamic limit is exact. Why? Because of this end here. Because the saddle point approximation in that limit becomes exact. Okay? Clear to everybody? So that's what we are doing. So mean field theory, stick this to your mind. Mean field theory is saddle point approximation. The two are connected. Now, this is the first, probably, I don't know, maybe you have already seen it, but this is probably the first time you see it. But when you will do something more complicated, like quantum field theory, in that case, mean field theory is the saddle point approximation. Okay? So the two things are one and the same thing. Can be reformulated one into the other. Clear? Great. Okay, so we are done with the saddle point. Next time, tomorrow, ground canonical ensemble. And then we will get towards very tough calculations. So be prepared. Cluster expansions, etc., etc.